where V is alpha prime 0. Okay, V alpha 0 is P, so everything happening at point P there. So V is alpha prime 0. So what we are interested in is the orientation vector field. So this is N. So this is, of course, here or here, it's all the same. So this is vector. Uh, N, whatever, N plus 1 at the appropriate point. Okay. So, so in other words, this, first of all, we need to, so these are functions now. So what is, if we have a smooth function f on the surface, not f, so usually f is reserved for the function which defines the surface. Okay, doesn't matter. So S is. So let's use some other letter there. H. This definition is quite the same. So this is, of course, going to be just delta, the gradient at the point P. So I am not writing the point P anywhere. So everything at P. So this is NTP. So here these all N1, N2, N3 are all functions, right? So the derivatives of the functions in the direction of V is defined like this. So these are called the derivatives of the vector fields that we are looking at in the direction of V. So for example, if you look at the coordinate directions, coordinate vectors, that is, if you look at, say, so this is just going to be the partial derivative. Because this is the directional derivative of the function in the direction of V. So this is the derivative in the jth coordinate direction. It's just the partial derivative there. So the derivative of a vector field is defined in terms of the derivatives, the directional derivatives of the functions which give you the vector field x. Now here, if you want, it is x1, x2, xn plus 1. So right now we are going to look at only the vector field n. So our definition of LP was so we want to see, first of all, where this object lies, right? We want to say, in fact, that it is in the tangent space. So in other words, we want to say that it is perpendicular to the normal, right? So take your n, look at n dot n. I'm omitting the arrows, okay? So n dot n is a scalar valued function, smooth, so on. So what is its derivative? how do you differentiate dot product? Usual product rule kind of. So derivative of this dot that plus this dot derivative of that. So of course here both are the same, so you are going to get two times this. But then n is an orientation vector field, so it's a normalized normal vector field. These are all unit vectors, right? So n dot n is 1, the constant function 1. So when you differentiate the constant function, you are going to get 0. Right? So what is the conclusion? This is 0. So that means del Vn is orthogonal to n. Okay? So or in other words, normal, orthogonal to the normal means it is tangent. This is also going to lie in the tangent space. So for any tangent vector v, LP of v is again a tangent vector, and therefore LP is a map from the tangent space to its TP. Right? But what kind of a map? Actually, you want it to be linear map because you are in a vector space. But linearity is not difficult to see from this. So what is, for example, see, F is right. So the components of this are all, so what is this? P n1, so on. Okay? So these are all functions. So this is going to be the gradient of n1 dot v plus w. So that is same as gradient of n1 dot v plus gradient dot w. So v and w can be separated. So this is so I can write plus w. So this is so this derivative is linear as a function of the vectors, tangent vectors there. As a function of v, this is linear. Of course, scalar multiplication also you can see much easier. So that gives you linearity of LP. And So on the tangent space at each point of the surface, you have a linear map like this. So this linear map is self-adjoint or symmetric, if you want to, because we are only in the real case. So it just means that inner product of LP VW is same as inner product V LPW. So this is just straightforward computation. Okay. Just move this up a little. Apply this del V. So this is LPV dot W. So you have to use product rule kind of, right? But then this part is going to vanish because this is orthogonal to the gradient vector field is orthogonal to the tangent space. So the first term will go off, and then when you compute the second term there, you will end up with something of this kind. The second partial derivatives, right? When you differentiate it once, you will get the first partial derivative there. When you apply the dot product there, and then now you have to, so you have to take the dot product of the whole thing with W, and then you will get one more partial derivatives like this. So you can do the same thing with the other one. The only difference is going to be the change in the order of taking partial derivatives. So here you will get del xi, del xj, and the other one you will get del xj, del xi. So in general, of course, you know, this may not be equal to this always, but if the function is sufficiently smooth, then this is going to hold. For example, if the function is C2 or something, continuously differentiable twice, if the second partial derivatives exist and are continuous, then they are going to be equal. Now for us, all functions that we are looking at are smooth functions, C infinity functions. So there is no problem about the equality of the mixed partial derivatives, right? The order in which you differentiate, it does not matter. So essentially, the self-adjointness of the Weingarten operator is a consequence of the fact that the mixed partial derivatives are equal. So once you have this fact that the operator LP is self-adjoint, you can invoke your linear algebra. Any self-adjoint or symmetric operator is what? Is diagonalizable, or what is the same? There is an orthonormal basis for the space consisting of eigenvectors of the operator. Yeah. So whenever, this is a finite dimensional case, so whenever you have an operator which is self-adjoint, there is an orthonormal basis for the space whose elements are all eigenvectors of the operator that you are looking at. This is what is called the spectral theorem, the finite dimensional spectral theorem. So what is that you are doing now in functional analysis? You have come to compact operators, compact self-adjoint operators, a spectral theorem for compact self-adjoint operators. Have you seen? Not yet, or you have? See, the result is valid and more generality. We are, of course, in the finite dimensional case, everything is nice, easy. The statement is true even in a more general setup. If you have a, let's say, just for convenience, let's say you have a Hilbert space and a compact operator on a Hilbert space, which is normal, or even self-adjoint is okay, good enough. Normal, you can even take normal if you want. So let us take a self-adjoint, compact self-adjoint operator on a Hilbert space. Then again, the space has an orthonormal basis consisting of eigenvectors of the operator that you are looking at. So, of course, the only difference is that in general, the set of eigenvalues may not be finite in a general Hilbert space. Nevertheless, the result is true that there is an orthonormal basis for the Hilbert space whose elements are all eigenvectors of the operator that you start with, which is compact and self-adjoint. Of course, if you drop compactness, then things are different. If you look at any bounded self-adjoint operator, then this is no longer valid. Compact operators are kind of generalizations or approximately finite dimensional operators. Okay. Of course, this in a Hilbert space, this is literally true. You can approximate any compact operator by a sequence of finite rank operators. Not true in general Banach spaces. This is a problem about the famous problem regarding this, but we will not talk about it now. Yeah, so but let me at least mention that if you drop compactness, the operator may not even have an eigenvalue, let alone talk of basis of eigenvectors. See, in the finite dimensional case, how do you get your eigenvalues? They are all roots of the polynomial, whatever that is, the characteristic polynomial, whatever it is called. And you know that polynomials have roots thanks to the fundamental theorem of algebra, all right? The complex case. Of course, in the real case, it's not true that you always have real eigenvalues. So, but you have complex eigenvalues. But if you are in the symmetric case, self-adjoint case, a real symmetric matrix will have real eigenvalues, no problem. But if you drop symmetry, then you may not have any real eigenvalues. But even in the complex case, the existence of eigenvalue, that any operator, any matrix has an eigenvalue, is a consequence of the fundamental theorem of algebra. So you need some complex analysis there. But in general, in the absence of finite dimensionality, this is no longer true. Okay, so there is no finite matrix in that case associated. There is no basis even in general, in any reasonable sense. Okay, but if you restrict to compact self-adjoint or compact normal operators, then there are always eigenvalues. Okay, in fact, the point is that the eigenvalues, in fact, even the spectral values are countable, and except possibly 0, all spectral values are eigenvalues. All members of the spectrum of the operator, except possibly 0 if or necessarily eigenvalues in the case of compact operators. Okay? But if you don't have compactness eigenvalues, even a self-adjoint, a bounded self-adjoint operator may not have any eigenvalues. For example, multiplication by, if you take L201, for example, look at the operator multiplication by function x, identity function, f going to x times fx, right? So this is a self-adjoint bounded operator. It has no eigenvalues. And self-adjoint also is important. Compact operators themselves may not have eigenvalues. The Volterra operator, for example. Again, take L201. Look at V of fx equal to 0 to x ft dt. This is a Volterra operator. This is a compact operator, not self-adjoint. So on V or on C01 if you want, on or L201, whichever you want. So this defines a bounded compact operator having no eigenvalues. Anyway, so what goes wrong? You see, in the finite dimensional case, when an operator, linear operator, you have the rank nullity theorem, right? So consequence of that is that if the operator is 1, 1, it is onto, right? Operator from the space to itself. Okay? If it is onto, it is 1, 1. So an operator is 1, 1 if and only if it is onto. This is no longer true in the infinite dimensional case. That's the underlying reason why you don't have this kind of thing in general infinite dimensional spaces. But anyway, so these are all beside the point that we are looking at. Just to say that the in the case of self-adjoint operators, you have a basis, an orthonormal basis made up of eigenvectors of the operator. That's the basic thing here. And you can actually explicitly, in this case, say what the eigenvalues are going to be. You look at the so in functional analysis, what is usually called as the it's enough if you look at that brings us to this quadratic form that we want to talk about. So you just look at this LPV. So this is a quadratic form defined by LP. Okay? If you confine yourself only to the unit ball, that is, you assume that the V is a unit vector. Okay, so we are in the finite dimensional case. The unit ball is a compact thing, and so on. So if you can look at, say, the maximum of this numbers, this function, the function of V, okay, a continuous function, the function of V. So you look at the maximum of this function on the unit sphere. Okay, so that is going to be an eigenvalue. Okay, and then you can proceed like this. So you take a corresponding eigenvector v1. Okay, so lambda 1, your maximum of this over the unit sphere, and then so call it lambda 1. That is going to be an eigenvalue. Take a corresponding eigenvector, and then what do you do? Look at the orthogonal complement of v1. So look at all vectors which are orthogonal to this one-dimensional eigenspace that you have. So you can restrict that to that subspace, the one dimension less than the original space. Okay? So you can look at, you do the same thing on that subspace rather than the whole space. So look at the orthogonal complement of V1, look at the same quantity, but now on the unit sphere on the subspace, the orthogonal complement. So that will again be an eigenvalue, and you can go on up to the stage n times or whatever times that you have repeat. So you get a whole set of eigenvalues, lambda 1, lambda n, not necessarily distinct. Okay? The maximum on the whole space can be equal to the maximum on subspace there. So you will get n eigenvalues and corresponding eigenvectors, which are all mutually orthogonal, by the way, right? The eigenvectors, you are taking the orthogonal complement. So any V2 in here is going to be orthogonal to V1. So you get an orthogonal basis. So you can normalize, of course, and get orthonormal basis consisting of eigenvectors of. So that, in fact, more or less gives a proof of the spectral theorem in the finite dimensional case. You use some analysis there and get this. So this operator LP, the Weingarten operator or Weingarten map, as it's called. I mean, this is what is. I haven't title potential. I didn't mention this. Okay, so we'll come to this in a moment. This is called the shape, of course. So it's called the shape operator because we'll see that it actually gives, in some sense, it measures the way this surface turns around the tangent at that point, or the normal at that point, both mean the same, is self-adjoint. Meaning, so as a consequence of this, in view of the spectral theorem, so you're going to have that. So TP has an orthonormal basis consisting of eigenvectors of LP. So this is true for every point P. The principal directions the eigenvectors eigenvalues They're all real, of course. We will arrange them in generally as increasing order of increasing sequence. Eigenvalues are called the principal curvatures of S at P. The determinant of the Weingarten map, determinant LP, is called the curvature, the Gaussian we denote it by K, the capital K at P. The trace of LP, trace of the Weingarten map is the mean curvature. It's called the mean curvature. Of S at P. So usually, yeah, H. Oh, by the way, so the corollary road is by the spectral theorem. Right? For self-adjoint operators on a finite dimensional space. So what is Kp? It's just the product of the eigenvalues, right? Of course, each of these are functions of P. I'm not, it's K1P, K2P, Knp. K is equal to K1, K2, Kn, and H is equal to, the trace is just the sum of these. Rather, I suppose, 1 over n times this is called the mean curvature. The average, right? Mean means average. So it's the average of all principal curvatures. So the form defined by the Weingarten operator, the bilinear form, that means if you take LPV dot W, so the bilinear functional of V and W, so this is a bilinear form on the tangent space. So V going to, right? So is a bilinear form on TP and is called the second fundamental form. Of S. Well, actually, usually only the quadratic form is called the second fundamental form by convention. So the corresponding quadratic form is second fundamental form V is LP V dot V, the quadratic form. Okay. So generally, only this quadratic form is called the second fundamental form, but it doesn't matter. Okay. When you take a unit vector, look at this second fundamental form at V. So this is Kp, if you want. I'm denoted by Kp. So this is called the normal curvature. Of course, the reason for this term normal curvature is the following. Probably I will mention it sometime later also. But so you have the surface, you take what is called the normal section of that surface. That means, okay, I will come to the normal section later, okay? But certain section of the surface is called a normal section. So when you take a planar section of a surface, what are you going to get? You will get a curve, right? A surface is cut by a plane in a curve. So the curvature, so this section is going to be through the point P, okay? A plane, an appropriate plane through the point P. So it gives you a curve which lies on the surface, of course. And then, so this is a planar curve. So you have what is called a curvature of a plane curve, right? So this object here, Kv, is going to be the curvature of that curve that you get at the point P. Okay, so the curve on the surface got by what is called the normal section of the surface at the point P. That is the normal curvature. That's why it's called the normal curvature. So it is curvature of a certain curve on the surface got by a normal section of the surface. So in terms of this normal curvature, so you can describe all your eigenvalues now. So the way I described earlier, you take the maximum on a unit sphere, okay? Maximum of Kv. So all this Kp, P is there always at the point. We are not mentioning every time. Over the unit sphere. So this is your Kn, the largest of the eigenvalues. Okay? And then the next one is go to, so V in Tp, of course. It's the same object, but now V in V1 orthogonal complement. So V1 is not V1, but let's say Vn, okay? It's now Kn, so where Vn is an eigenvector corresponding to, so LPVn is KnVn, okay? So Vn is a unit vector, unit eigenvector for. So this is the maximum of the same thing. Of Kv. So on, right? So the first eigenvector K1 is going to be what? It's going to be the minimum of what will be the easiest example of a surface is the plane. Of course, only then you get the sphere, right? Sphere is a normal one because the plane is plane, so it's not really a surface that you imagine. But anyway, so plane, sphere. Let's see what these are. What the Weingarten map is, right? So what is going to be if you take a plane? So what is the Weingarten map? You know what this is? You can write n itself, okay? So n itself is 1 over so on this we have done repeatedly. So what is this is what P right? But what are these now? N1, I mean, there is only 3 of them now. So N1, N2, N3, okay? So N1, N2, N3 are all constants now, ABC over something. So when you differentiate, you're going to get zeros, right? Which means the Weingarten map is the 0 map. Correct? So nothing to talk about, right, in this case. Because, I mean, the plane doesn't turn anywhere, so it remains the plane. So the curvature is going to be 0. All things are 0, right? Kj equal to 0 for all j, so k equal to 0, so on. What about the sphere? Let's take, for a change, let's take a sphere of radius r or something. We can take an n-dimensional sphere if you want. It's the same thing, okay? So now you have to fix the orientation, that is, fix the normal direction. If you take the inward normal, for example, So what are the two normal? So you have only one normal, either outward or inward. So outward is now it's not 1, so we will have q over r now, or minus q over r. Q over r will give you the outward normal, minus q over r will give you the inward normal. So if you take the inward normal, say, this is the inward normal. When you normalize, you will get this factor r here in the denominator. So what is this now? What is del v of n at any point p? Is going to be p. So what are you going to get? P dot v. So you see, what are the components here? You are going to get right? This is what it is. This one. Okay. But what are these? The components are x1 with a minus sign, x1, x2, xn, x whatever, xn plus 1. If you are taking this case, otherwise x, y, z. So you will have. So this is what del v nj is going to be del v with a minus sign there with xj, right? The coordinate functions. So this is going to be del f del f means xj, okay, dot v. But gradient of the coordinate functions are the partial derivatives. So partial derivative of the function, identity function x. So this is the identity function here, okay? So you're just going to get r varum, yeah. I'm n, because I'm just writing this, then we will divide by r, okay? So you will just get vj, right? Jth coordinate. So you will just get q or p, whatever it is, with a minus sign everywhere, v1, vn. Okay, so divided by r, 1 over r, and then you have, so this is delta v of h is delta of h dot v, right? So you're going to have lp of v. There is one more minus, so that's why I took the minus there, the inward normal rather than the outward normal. You just get the identity function multiplied by r, 1 by r. If you take outward normal, you will get minus 1 over r times that. So the curvature will be 1 by r, right? Curvature generally means Gaussian curvature. Okay. So the curvature of a sphere is the reciprocal of the radius. So this, in some sense, you see, conforms to our perception. If you have a small sphere, it curves more, right? If you take a large sphere, locally it looks more or less flat, right? The surface of the earth, for example, that we are standing on, so we perceive everything to be flat, more or less. So because the radius is quite large. So larger the radius, smaller the curvature.